So today I will start this class from a completely different perspective. As of now, we have seen that in the last few classes we have talked about the notion of signals, notion of systems, and the behavior of a special type of system, in particular LTI systems, right? Linear time invariant systems, or in more generic case we can call it linear shift invariant system or LSI system. And in our case, when the signal is considered to be a function of time, then it is a linear time invariant system. Now you have noticed that the characteristics of such a system, LTI system, can be obtained just by performing a single experiment. As we have discussed last day, as we mentioned last day, that if you perform only one experiment on the system, you will know everything about the system, right? And that experiment is that you just excite the system with an impulse function, unit impulse function, find out the impulse response, h of t for continuous time systems or h of n for discrete time systems. And once you know h of t, once you know h of n, then you know everything about the system. For example, you know whether the system is a stable one, stable or not, whether the system is a causal system or not, or anti-causal or not, and what else. Now, you have perhaps noticed that for LTI system, the output can be regarded or can be represented by virtue of a particular mathematical formula, and that formula or that mathematical expression is known to be in convolution integration, right? Convolution integration for continuous time system and convolution summation for discrete time system. For example, if I have, say for example, I am having this signal x of t, and this signal is applied to an LTI system which is characterized by its impulse response h of t, and you have noticed that this output y of t is regarded as the convolution integral between x of t and h of t. That's all. Now, while receiving at this particular range, what we have actually done, we have represented that signal x of t as a weighted summation or as a weighted integration of a number of impulse function, right? Impulse and its delayed version. We have represented in that particular way, isn't it? So, as of now, what we have done, we have represented the signal, any arbitrary signal x of t or x of n, as the weighted accumulation of impulse and its delayed version. Right? So, what we have done actually, we have represented this x of t as integration going from minus to plus infinity x of tau del t minus tau d tau. In this particular form, we have represented x of t is equal to integration going from minus to plus infinity x of tau del t minus tau d tau. That means we have delta t function, unit impulse function, and we have allowed this delta t function to range from minus to plus infinity. That's why delta t minus tau, where tau is ranging from minus to plus infinity, and the corresponding weight is given by x of tau. Right? So we are representing that particular manner. And what we have ultimately arrived at is that we have found out that the output of such a system is regarded as the convolution integral or convolution summation between the input signal x of t and the impulse response h of t. So that is the story as of now. Now, as I have started today's lecture from different perspectives, that today we will observe the signal from another perspective. And perhaps you have noticed that this impulse function, while we have discussed about the different types of functions in terms of system signals in my very first or second lecture, I have mentioned that impulse function is a kind of function that means it exists only for a very small amount of time, tau tending towards 0, and if we just calculate the curve, that is going to be for unity impulse function, that is unity. That means the height is approaching towards infinity, the width is approaching towards 0, so that the area under this curve is approaching towards unity. And that's a very peculiar function, impulse function, right? On the other hand, if you just consider a sinusoidal function, so sinusoidal function is something like, for example, if you consider a sine omega t, for example, this sinusoidal function is a periodic function, you know, and it will exist for all t. Periodic function. Let's say a sine omega t ranging from minus to plus infinity. So at one end, you have impulse function, and hopefully I have also mentioned that impulse function is a kind of function which consists of all the frequency component. Although I have not formally introduced what is meant by the frequency, but hopefully I have introduced that term. That impulse function is a kind of function which contains all the frequency components in equal proportion. And sinusoidal signal is a particular type of signal which consists of a single frequency, single tone. Monotone, monotonous, monotone, single tone. Mono means one, tone means frequency. So here lies the tussle between these two functions. One is sinusoidal function and second one is impulse function. The impulse function consists of all the frequencies available in the universe from minus to plus infinity, all the frequencies available in equal proportion, right? And on the other hand, the sinusoidal function, sinusoidal signal, it consists of a single frequency, a sine omega naught t. It consists of a single frequency omega naught. Omega naught is equal to twice by f naught. F naught is the Hertz frequency, as you know. Only one frequency. So sinusoidal signal will consist of a single frequency, and the impulse function will consist of all the frequencies available in the universe in the equal proportion. Now, as of now, we have observed the signal as I've also written over there. Any signal x of t can be regarded as the weighted summation or weighted accumulation of the impulse and its delayed version. Right. Now today we will observe this signal from a different perspective. Now let's assume that okay, the signal that I'm going to apply is not represented as the weighted summation of the impulse and its delayed version. Suppose the signal that I'm going to apply is a complex sinusoid. Just the opposite. Just the opposite. Let us apply a signal which is a complex sinusoid. So for example, what I mean to say is, now I would like to have a signal x of t. This x of t is given by e to the power j omega, or let it be say j omega naught t, something like that. X of t is equal to now e to the power j omega naught t. So it's a complex sinusoid. X of t is equal to e to the power j omega naught. You can also add some scalar factor outside. That means a times e to the power j omega naught, but doesn't make any difference. So what I want to emphasize is that x of t, the signal that I am going to apply now, is not regarded as the weighted summation or weighted accumulation of the impulse and its delayed version. Rather, it's a complex sinusoid, e to the power j omega naught t. And once again, the signal is being applied to an LTI system with impulse response given by h of t. Okay. Now, had this been the case, so you will be able to find out this y of t. So this is applied. This is applied to an LTI system. LTI system whose impulse response is given by h of t, and we are interested in finding out the output signal y of t. So what is y of t? What should be the formula for that? This is simple convolution, as you know, because it's an LTI system. So the input-output relationship is given by the convolution. So minus to plus infinity you can write like x of tau ht minus tau d tau, or as the convolution operation is commutative in nature, so you can also write it down something like that, h of tau x of t minus tau d tau. So if I consider the second form of the integration, minus to plus infinity, h of tau, and x of t is basically e to the power j omega naught t. Okay. So what is x of t minus tau then? E to the power j omega naught t minus tau d tau. Right? Now you look, this integration is carried out over tau. Tau is a variable, isn't it? H of t, x of t minus tau d tau. So the range, so this limit is for tau, minus to plus infinity. This is for tau. So e to the power, as you know, e to the power j omega naught t minus tau can be represented as e to the power j omega naught t multiplied with e to the power j omega naught minus tau, or minus e to the power j omega naught tau. So this e to the power j omega naught t can be taken outside. It can be taken outside because it's a function of t, it's not a function of tau. So what I can write is e to the power j omega naught t, and then the rest of the integration, minus to plus infinity h of tau e to the power minus j omega naught tau d tau. And here we arrived at a very interesting observation. Just take a look at this particular thing. So what we have got? We have found out that y of t is equal to e to the power j omega naught t multiplied with minus to plus infinity h of tau e to the power minus j omega naught tau d tau. And let's segregate this one. So what we have applied? We have applied e to the power j omega naught t at the input to the system, x of t, right? We have applied e to the power j omega naught t. What we are getting? We are getting y of t. What is that? This is basically this e to the power j omega naught t, the signal that you applied, multiplied with something. And this something is a function of what? This something, this entire thing which I have marked with this green box, what is that? Is it a function of what? Which parameter? You know, it's not a function of tau. We have considered all the values of tau from minus to plus infinity. It's a function of omega naught. It's a function of omega naught. For different omega naught, you'll be having different integration, right? So what I can write this y of t as e to the power j omega naught tau, j omega naught t multiplied with h of omega naught, something like that. Capital H of omega naught, which is given by minus to plus infinity h of small h of tau e to the power minus j omega naught tau d tau. The integration is a function of omega naught, because if you change omega naught, it's having different integration value, because you have considered the all values of tau from minus to plus infinity, all possible values of tau. Now that's a very interesting result. We have applied the signal x of t, that is equal to e to the power j omega naught t. In return, what I am getting is the signal back multiplied with some constant, which is a function of omega naught, obviously. And this type of signals, when applied to a system, is returned, or this type of functions, a type of function, when it is applied to a system and it is returned as it is, multiplied with some constant. This type of functions or this type of signals are known as the eigen functions or eigensignals. Eigen. These are known as eigen, E-I-G-E-N, eigen functions. So for this LTI system, characterized by its impulse response h of t, what is the eigensignal, what is the eigenfunction? E to the power j omega naught t. That is the eigenfunction. Because if you apply e to the power j omega naught t to this system, having impulse response given by h of t, then in return, you are getting this back. You are getting this back, right? Multiplied with some constant, and that constant is a function of the frequency of that particular complex sinusoid. When I call it e to the power j omega naught t, this is basically, you can represent by virtue of the Euler's formula, cos omega naught t to the power jx, you know. What is the formula for e to the power jx? cos x plus j sin x. So basically, what you have one complex rotating phasor which is rotating at an angular frequency of omega naught. Right. So therefore, the frequency of this particular signal e to the power j omega naught in this complex exponential complex sinusoidal function is given by omega naught, capital omega naught. Okay. And when you have applied this signal e to the power j omega naught t to this LTI system, in return, what you are getting the signal back e to the power j omega naught t multiplied with some constant, and that constant is a function of, basically it's a function of two parameters. One is obviously it's a function of h. For different LTI systems, for different h, you'll be having different capital H, and obviously it's a function of omega naught. Right. So this h of omega naught, this h of omega naught, it's a function of two parameters. It's a function of the system itself, and it's a function of this omega naught that you have applied. But the bottom line is that you have got the signal back e to the power j omega naught. You have got it back. Similarly, so that is the scenario for the continuous time case. Similarly, for the discrete time case, you can also check. For discrete time case, what we are going to apply? We are going to apply x of n. So I will refer this continuous time case and the discrete time case side by side. This is basically e to the power j, and that is a discrete frequency small omega naught. It's not the capital frequency, capital omega, it's a small omega, e to the power j omega naught. Okay. So this is applied where? This is applied to an LTI system. This is applied to an LTI system whose impulse response is given by h of n. In return, what you are getting? You are getting y of n, and that y of n can be represented as x of k, h n minus k, k going from minus to plus infinity, or since the convolution operation is commutative in nature, you can also represent this by x h of k, x of n minus k. Okay. So what is y of n then? So this y of n is given by summation k going from minus to plus infinity. You write like h of k there, and then you have e to the power j omega naught n minus k. Okay. Any doubt up to this? Anybody having any doubt? Same formula, h of k e to the power j omega naught n minus k, and the summation is over k. So I can take this one outside. I can take e to the power j omega naught n outside, and I'm left with k going from minus to plus infinity, h of k e to the power minus j omega naught k. So e to the power j omega naught n. So once again I'm getting it back, and I call this as h of omega naught. What is h of omega naught? Summation k going from minus to plus infinity, h of k to the power minus j omega naught. So even for the discrete time case, I am getting it back. Even if it is it is not e to the power j omega t, rather e to the power j omega naught n, I am getting it back. So for this system, LTI system, whose impulse response is given by h of n, e to the power j omega naught, e to the power j omega naught n can be considered as its eigenfunction. That means if you provide this as the input, it is very easy for you to calculate the output. Last time when we have represented the signal, any arbitrary signal xt, as the weighted summation for discrete time case, as the weighted summation of the impulse and its delayed version. That time you have to rely on what? That time you have to rely on the convolution integral. We have represented x of k as summation k going from minus to plus infinity, x of k delta n minus k. And accordingly, you have applied the properties of additivity, you have applied the properties of homogeneity, you have applied the properties of time invariance. And then what you have got is h of y of n is basically summation k going from minus to plus infinity, h of k, x of n minus k, or k going from minus to plus infinity, x of k, h of n minus k. That means you have to rely on convolution operation. And remember, convolution is a combination of different small operations like folding, then shifting, then multiplication, then addition. That's a kind of tedious operation over here. But instead of representing the signal as the weighted summation of the delta function and its shifted version, now I can represent the signal. Suppose I am allowed to represent the signal as, say, as an eigenfunction only. Suppose my signal is an eigenfunction, e to the power j omega naught t or e to the power j omega naught n. And you apply this signal to an LTI system with impulse response h of t or h of n, as the case may be. Then it is very easy for you to calculate the output. You just multiply, the signal is obtained because it's an eigenfunction, so you get it back. You get this e to the power j omega naught t back or e to the power j omega naught n back. Multiplied with something, and that something is a function of the system itself and the frequency of the signal that you have applied. So that makes the, not only it will give you a defined perspective, a defined dimension of understanding, but that makes you the calculation very easy for you. Isn't it? That makes the calculation very easy. Now the question is, having said that, so before I proceed further, let me ask, how many of you have understood this concept as of now? What is the need of representing this x of t something? How many of you have understood this properly? No one? Yes or no?
Yes.
You understood this one, this particular concept properly? If you can understand this, then you can proceed further. Last day we have represented the signal as the weighted summation of delta function, and this time we have observed the signal as a single e to the power j omega naught. That is known to be the eigenfunction. Right? That is known to be the eigenfunction for the system under consideration. Right? I believe that you have eigenfunction in your in mathematics class you have studied, na? Eigenvalues and eigenvectors you have studied. So this term eigen is not known. I think it is not new to you. It is already known to you. It is not an unknown quantity to you, right? So that is the basic significance of the eigenfunction. And eigenvectors you already calculate eigenvectors and all this. Okay. Any doubt? Okay. So, what we have observed? We have observed that, okay, we have got one e to the power j omega naught t. Let us come back once again to the continuous time case, e to the power j omega naught t, capital omega naught, right? And remember this e to the power j omega naught t, this particular thing, obviously, since it involves this cos and sine, it's a periodic signal, right? E to the power j omega naught t. It's a periodic one. Now, there is no such guarantee that your signal is always like a sinusoidal signal. A complex sinusoid might not be. But suppose I would like to represent my signal. I would like to represent my signal not as a summation of the delta function that we have done for the last few classes. Rather, now I would like to observe the signal from a different perspective. I have noticed that if I represent the signal as a single sinusoid, single complex sinusoid, then it is very easy for me to calculate the output signal. Right? So therefore, let us try to represent the signal, any arbitrary signal, as a summation of weighted complex sinusoids. Can you get my point? Instead of observing the signal as the weighted delayed version of the data function, let us try to observe the signal, any arbitrary signal x of t, as any arbitrary signal x of t. Let us try to visualize this x of t, any x of t, as it is summation over k, summation over k, ak e to the power j omega k t. So we have started with a single eigen function, that is e to the power j omega naught t, only one complex sinusoid. But your signal can be anything. There is no such guarantee that your signal is always a sinusoidal signal. It can be anything. So any arbitrary signal, you can have any arbitrary signal, right? And I'm observing the signals something like that. Summation over k. Summation over k. I'm not saying how many such k's are required over there, but summation over k. Some k's will be there. Ak e to the power j omega k t. Can you understand what is meant by this? Ak e to the power j omega k t. You have one particular k. Let's consider k is equal to 0. Our previous case, omega naught. Consider k equal to 1, omega 1, k equal to 2, omega 2, k equal to 3, omega 3, something like that, or minus 1, minus 2, minus 3, and so on and so forth. So any complex sinusoid, kth complex sinusoid, having frequency called omega k t, omega k, so represented by e to the power j omega k t, multiplied with the weights, that weight is given by ak for the kth sinusoid, and let's add them together to get the final signal x of t. I don't know whether I'll be getting this or not, but let's take this approach. Is it okay? Summation over k, ak e to the power j omega k t for the continuous time case, and for the discrete time case, you represent this like x of n is equal to summation over k ak e to the power j small omega k t. Sorry, omega k n. So x of t is represented as summation over k ak e to the power j omega k t, and x of n is represented as summation over k ak e to the power j omega k n. I really don't know whether it is possible to represent in this particular form or not, but let's have something like that. Let's have a try. Okay. So I don't know whether you'll be getting x of t actually or not. You don't know. You have some x of t. That x of t can be represented in this particular form, maybe, may not be. So this is a kind of approximation that we are going to achieve. So let's call this approximation as hat, x hat t and x hat n. Our actual signal is x of t, right? And I'd like to visualize this x of t as the summation of these complex sinusoids in the continuous time domain or in the discrete time. Here. Now, based on the type of the signal that I am dealing with, whether, so you know that there could have been two different types of signals. Either you can have a continuous time signal or you can have a discrete time signal, right? And from the since the signal, the basis signal, there's another term I'm now referring to. It's known as basis signal. What is basis? We have studied the vector algebra. You studied, no? Vector algebra you studied. So suppose you would like to represent any vector in a two-dimensional scale. So what are the basis functions? What are the basis signals? The unit vectors, right? The I and the j. Say 2i plus 3j minus 5i plus 6j. So these I and j, these are the basis, because based on which you can ultimately reconstruct the, you can ultimately represent the signal. The basis signals. So basic signals are basically the basic components, constituents of the signal itself. So here we can consider this e to the power j omega k t or e to the power j omega k n as the basis functions or eigenfunctions also. So whether using these basis functions or basis signals you will be able to represent the signal or not, but the one thing is very sure is that these signals, basis signals, these are periodic. These are periodic in nature, isn't it? So based on that, since I have started my discussion from different types of signals, continuous time and discrete time, as you know. Similarly, the basis signal I am considering over here, the eigenfunction I am considering over here, since it's also a periodic signal, as you know. So based on that, I can also, because I don't know whether the signal under consideration, the signal that will be applied to the LTI system, there is no guarantee that the signal is guaranteed to be periodic. It can be aperiodic also. So based on that, I can also have two types of signals. One is known as the periodic signal, second one is known as aperiodic signal. So your xt can be periodic, your xt can be aperiodic. Your signal can be discrete time, x of n, can be continuous time, x of n. So accordingly, you have four different combinations. One is continuous periodic, second one is continuous aperiodic, then the discrete periodic, and the discrete. Right. So what is the basis? Because once you study continuous, because this course is on signals and systems, so from analog domain to the digital domain, from continuous domain to the discrete domain, so we have to refer to these types of signals side by side. X of t along with x of n, because this course is not on DSP. At this course is on DSP. In that case, we will be referring only to the discrete time signals, digital signals only. But since this is a basic course and generic course, so when I refer to any x of t, any continuous time signal, side by side, I need to refer to the discrete time signal, right? And since the basis functions that or the eigenfunctions that we are dealing with over here is basically a kind of periodic signals, and you know that the signal that I am going to apply cannot be periodic always. It can be periodic, can be aperiodic. So there is a basic question that must come to your mind, that whether is it possible for any aperiodic signal to be present in this particular form. So let's categorize the signal into two different classes: periodic signal as well as aperiodic signal. So we have four types of signals: continuous periodic, discrete periodic, continuous. And for the next 1 or 2 lectures, I will restrict my discussion on periodic signals, and then we will move to the aperiodic signals. So periodic, continuous as well as discrete. Okay. So the signal under consideration is a periodic signal. So x of t, x of n, both of them are periodic as of now for the next few classes. And then we will definitely refer to the aperiodic signals as well. Now, if the signal is a periodic, suppose x of t is a periodic signal, right? And the period is given by say capital T. Capital T is the period, right? Now the question is that this type of representation, whether this type of representation can be, whether it is able to represent the signal properly or not. So that can be judged on criteria, and that criteria is known as the mean square error criteria. What is that mean square error? So I would like to find out the mean square error MSE criteria. MSE criteria. I would like to find out the MSE criteria for the continuous time case, and that MSE is given by the difference between the original signal and the represented signal. Their difference squared and integrated over the entire period. Mean square error. So you have to find out the error. What is error? Error means the actual signal x of t and the represented version x cap of t, x of t and x cap of t. So their difference is x of t minus x cap of t or x cap of t minus xt. Signals can be real signal, can be complex signal as well. So we have to take the modulus, right? Then square it and then find out the mean. And based on that, this is given by, so what I would like to mention is integration x of t minus x cap of t, that is error signal, x of t minus x cap of t, mod square error, right, and find out the mean. That means integrate over all t from minus to plus infinity, and sorry, it should not be from minus to plus infinity because the signal is periodic under consideration. So it will be over a period 0 to t and 1 by t. Had this been a periodic signal, then you have to go for minus to plus infinity. Since it's a periodic signal, so you have to consider only one period. Right? 1 by t integration 0 to t mod xt minus x cap t whole square dt. This is the case for the continuous time signal. Similarly, for the discrete time case, this MAC is represented by 1 by n. Now, instead of having integration, you'll be having the summation x of n minus x cap of n mod square. Say n is from 0 to n minus 1. That is the period is n. After every n samples, the signal gets repeated. Right? So that is the MAC expression. And you have to check whether this MAC turns out to be 0 after the signal representation is over. Right? Okay, so as I've told you, I will today I mainly focus on the periodic signal, only periodic signal, continuous and as well as discrete. So the thing is that, suppose let's consider a signal which is having a period of capital T. So you can have any type of signal. You can have a sinusoidal signal, a periodic one, a rectangular signal. You can have a triangular signal. You can have a short type of signal, any kind of signal. So they are defined as a periodic signal. Let me just give you some of the diagrams. For example, this can be a periodic signal. This can be periodic signal. This can be periodic signal. So they could have been defined as a periodic signal, right? X of t. So in the description of this x cap of t, what we have mentioned is it's basically summation. It's basically a summation over k and ak e to the power j omega kt. Right? Now the thing is that your signal x of t is having a period of t, capital T. X of t is having a period of capital T. So therefore, if you just consider the components of the signals, what are the components of the signal x of t? What are the components of the signal? Basically, they are the complex exponential signals, complex sinusoids. Complex sinusoids. So therefore, the period of this complex sinusoids must also be the same, right? So if the period of one signal, period of your actual signal x of t is capital T, then the period of the other signals, the constituent signals, should be t, or you must be knowing what is the formula for a periodic signal. X of t is equal to x of t plus capital T for all t. That is the formula. X of t is equal to x of t plus capital T for all t. That is the formula. If you can remember it properly. So x of t is equal to x of t plus capital T for all t. That was the formula. periodic signal. So had this been the case, since it is true for all t, can I put in place of small t, can I put t plus capital T? Yes, I can put that. I can also put that. Suppose you have one signal, something like that. This is one signal. So this is T, this is 2T, this is 3T and so on. This is T by 2, this is T, this is 3T by 2, this is 2, this is another signal. Both of them are periodic. First signal is periodic with a period equal to capital T. Second signal is also periodic. It gets repeated after every T by 2. Or I can also say it gets repeated after every T. After every T, this gets repeated. In that case, you consider this entire thing. You consider this entire thing as one block. Right? So this gets repeated after every T. Something like that. Or you can break it down, even further. Right. So the constituent. So I know that my signal that I am going to represent, the signal that I am going to represent is having a time period of capital T. So the constituents are what? The constituents are complex sinusoids, right? And their periods is capital T and as well as if I just consider the frequency. So what is the frequency? What is the Hertz frequency? That is the 1 by T. 1 by T is Hertz. If the signal time period is capital T, Hertz frequency is 1 by T. So the constituents, the different complex sinusoids, if I just consider the corresponding Hertz frequency, this omega, as you know, omega is equal to 2 pi into the Hertz frequency. Omega k is equal to 2 pi Tft, or 2 pi by capital Tk. So the constituents, the eigenfunctions, eigenvalues, they have the frequency equal to the frequency of the original signal that I am going to represent, as well as all the multiples of that particular frequency. All the multiples. All the possible multiples. Right. So therefore, you know that this. Okay, let's start with this digital and analog frequency omega k is given by 2 pi fk, which is given by 2 pi by tk. Okay. So the signal that I am going to represent is x of t having a period is equal to capital T is represented as summation ak e to the power j omega kt for k ranging for different case. Now the story doesn't end here. Now I need to find out what is the relation between this omega k and omega k minus 1. Omega k minus 1, omega k minus 2, because these are not the simple omega k's. You have to maintain that this constituent basis functions or constituent eigenfunctions, they must be having the frequency which is the multiple of the original signal frequency. What is the original frequency? What is the original signal frequency? That is let's call the original signal frequency is say f naught. That is the f naught is the original signal frequency, which is given by f naught, which is given by 1 upon t naught, and this omega naught is equal to 2 pi by t naught. That means 2 pi f naught. That is the original signal frequency. That is the t I am mentioning. That's that t or t naught over here on single period. So therefore, the constituent eigenfunctions, their frequencies, their Hertz frequencies must be the multiple of the original frequency. So this omega kt can be represented as k times omega naught. So instead of writing this simply as e to the power j omega kt, what I am referring is ak e to the power j k, sorry, this will be capital omega j k, it will be capital omega naught t on k. Now gradually I am just heading towards the intended formula. I have started with, if you can remember, I have started with a single complex sinusoid, right? E to the power j omega t. And then we have accumulated a number of complex sinusoids. Summation over all k, ak e to the power j omega kt. Omega suffix k. And then we have emphasized that since the signal under consideration is having a time period of capital T naught, so therefore the constituent basis functions or constituent eigenfunctions, they must be having a frequency which is the multiple of the original frequency. So therefore I have represented like x of t is equal to summation over k a to the power j k omega naught. Okay. What is the scenario for discrete time case? For discrete time, this is the scenario for the continuous time. For the discrete time, it's pretty easy. You might say that okay, x of n is equal to summation over k ak e to the power j omega k n, that is equal to summation over k ak e to the power j k omega naught n. Okay. But remember, although it looks very easy, pretty easy, these two expressions, x of t and x of n, there is a certain difference. What is the difference? Where is the difference? The discrete frequency that we have considered over here, this omega k, capital omega k, this capital omega k is for analog frequency. This is capital omega k, analog frequency, and this small omega k is the digital frequency. This is capital omega k, analog frequency, small omega k, digital frequency. So this capital omega k is represented as, we have represented this capital omega k as multiple of the fundamental frequency, and these are known as the harmonics. Omega naught is the fundamental frequency. Omega naught is given by 2 pi f naught. F naught is the Hertz frequency, and omega naught is known to be the angular frequency. So these are known as the fundamental frequency, the frequency of the signal that I am going to decompose, x of t. And this omega k, which is represented by k times omega naught, omega k, they are known as the harmonics. Suppose you would like to represent one signal whose frequency is equal to say 10 Hz. Okay, you have one signal whose frequency is equal to say 10 Hz. Now what you can do is that you have got 10 Hz signal, one 10 Hz sinusoids, any 10 Hz signal, any 10 Hz periodic signal, not necessarily sinusoid, any 10 Hz periodic signal. So you have got one 10 Hz sinusoid, then another 20 Hz sinusoid, then 30 Hz sinusoid, 40 Hz sinusoid, 50 Hz sinusoid, and so on. So all the high frequency components. So first harmonic, second harmonic, third harmonic, fourth harmonic, so on and so on. Okay. So that is pretty easy for the analog frequency or the capital omega k. But this is because, and these distinct frequencies omega k, they are distinct in nature. And in analog domain, these frequencies are distinct in nature. But that is not the case. That is not the case with the digital frequency. What we have represented, this omega k, I can represent like k times omega naught, okay, that's fine. But this discrete frequency, so whatever we have got is basically e to the power j k omega naught n. Remember, this is this e to the power j k, although e to the power j k omega naught is distinct in nature, but e to the power j k omega naught n, they are n periodic in the frequency index k. I am trying to emphasize. You have got e to the power j k omega naught n. That is your constituent basis function. That is the constituent eigenfunction. E to the power j k omega naught n. That is not to be the kth eigenfunction. Right? But they are not distinct. They are n periodic in the frequency index k. What is meant by that? You have got e to the power j k omega naught n. Now, I am mentioning that this is n periodic. So therefore, let us try to check whether this is periodic or not, whether this is n periodic or not. So if I write it down, e to the power j k plus n omega naught n. What is that? E to the power j k omega naught n, that is the signal, that is the basis function, that is the your eigenfunction. Now I have said that this is not distinct. This is not distinct. After a few samples, it gets repeated. So I have said that it is n periodic in frequency index k. That means after every n samples, this gets repeated. So from this, if I advance by n samples, it is about j k plus n omega naught n. And if I now simplify this one, what I am getting? E to the power j k omega naught n back, fine, multiplied with e to the power m plus n, e to the power m into e to the power n, right? E to the power j n omega naught n, right? What is omega naught? What is omega naught? 2 pi by n. So therefore, this e to the power j n omega naught n, ultimately it gives to, what is the value? E to the power j n omega naught n. What will be the value then? It gives you to 1. It will be n omega naught is how much? 2 pi. E to the power j 2 pi. How much? 1. So this is equal to e to the power j k omega naught n. So although we have started with e to the power j k omega naught n, but we have noticed that this particular basis function or this particular your eigenfunction is not distinct. After every n samples, it gets repeated. Isn't it? It's a periodic signal. It's a periodic signal with period equal to n. So while writing the summation sign for the discrete time case, we have written like summation over k. But we have never mentioned how many such k we can consider for discrete time case. For continuous time case, you don't have any problem. Right? But for discrete time case, you have a limit. You understand this in a much better way when you study the discrete frequency or digital frequency, digital signal processing course. Because for the digital frequency, for the discrete frequency, there is a repetition, there is a maximum limit. For continuous frequency, you can go from tens of hertz to a few gigahertz or terahertz. Nobody can stop you. But for the digital frequency, after every 2 pi rad per sample, there is a repetition. And that makes a difference. So therefore, for digital case, you cannot consider all such things. Rather, you have some limitations, you have some restrictions. And since it's a n periodic signal, so how many such samples you can consider? How many such frequencies you can consider? How many? After every n, it gets repeated. So, in the previous slide, what you have mentioned, this one, is x of t is okay, there is no problem with that. But for this x of n, we have considered summation over k, ak to the power j k omega naught n. But remember that k is not infinity, it's not from minus to plus infinity. Because after a few samples, after every n samples, this gets repeated. So we have certain limitation on that.
But AK doesn't repeat.
AK doesn't repeat, but you have the same signal, so the same basis function you are getting. Doesn't make any sense. What is our objective? Our objective is to represent the signal. I mean, even if you have some AK and AK plus n, so that can be considered together as a different AK dash, something like that. What is our objective? Our objective is to visualize the signal as the different sinusoid, different complex sinusoids. Right? But after every n samples, this jk omega naught n gets repeated. So therefore, this summation is not for all k. However, this is for all k. So this x of n can be regarded as, so how many such samples, how many such distinct frequencies we can consider? N number of such, right? So k is from 0 to n minus 1, typically from 0 to n minus 1. Ak e to the power j k omega naught n, right? And this x of t, for this one you don't have any problem. For x of t you don't have any problem, because there you can consider all the frequency components, because there is no such repetition. There is no, so all the frequency components, they are distinct in nature. So here you consider for all k, ak e to the power j k, this is capital omega t. That is a representation of the signal in this particular form. Is this okay? Any doubt up to this? Any doubt up to this? No doubt. This x of t, or rather x of n, let's start with the discrete time case. X of n as summation k going from 0 to n minus 1, ak e to the power j k omega naught n for a periodic discrete time signal, where xn is periodic and obviously discrete, quite obvious from the nomenclature itself. So out of these four different combinations, continuous, periodic, aperiodic and discrete, now we have considered the periodic discrete case, and this representation is known as discrete time Fourier series representation of any arbitrary signal. This is known as the discrete time Fourier series representation, named after Joseph Fourier. Discrete time Fourier series representation of any arbitrary signal xn which is periodic in nature, having a period is equal to n. What are those AKs? These are the corresponding weights associated with the kth complex exponential, complex sinusoid. This one. Similarly, you can also have continuous time Fourier series representation for continuous and periodic. Okay. Now the question is that why are we interested in finding out or representing this x of n in this particular form? What does that mean? Basically, what you have got, if I have only one frequency over there, for example, if I have only one frequency like ak e to the power j omega kn, this is provided to the input to a system which is having an impulse response given by h of n. What is the output? What is the output? X of n multiplied with h of omega k. Right? H of x of n multiplied with h of omega k. If this is your x of n, suppose this is your x of n. Now what I have not only a single complex sinusoid, I have a number of complex sinusoids, n number of complex sinusoids. Right? So therefore, if I invoke the property of additivity over there, because it's an LTI system, so let us invoke the property of additivity. So for ak e to the power j omega kn, this is output, xn multiplied with h omega. For example, if it is omega 0, xn e to the power xn h omega 0. If it is omega 1, xn h omega 1. Omega 2, xn h omega 2. Now if it is like a0 e to the power j omega naught n plus a1 e to the power j omega naught n plus a2 e to the power j omega 2n plus a3 e to the power j omega 3n plus a4 e to the power j omega 4n and so on and so forth, then it will be summation of the individual outputs. Because it's an LTI system. Can you get my point? And that makes your calculation and understanding in a much elegant, easier. Instead of representing the signal as the summation of the delta, we have represented the signal as the accumulation frequency components. And you can always visualize in practical sense, you can always visualize the frequency from a different perspective also. For example, whenever you are standing in a queue while catching metro, say for example, let us try to personify you as a signal. So you are the signal. Let us try to personify the signal itself. So as I've mentioned over there, signal is having different frequency components, right? One is omega 1, second is omega 2, omega 3, omega 4, omega 5, and my signal is composed of, say, n number of such omega k. Omega k is ranging from 0 to n minus 1, omega 0, omega 1, omega 2, omega 3, up to omega n minus 1. Now, you be the signal, you can also be constituted as the different components. What are those components? They are different perspectives. Your educational background can be regarded as one attribute. Your societal background can be regarded as second attribute, right? Your cultural background can be regarded as a third attribute. Your financial background can be regarded as a fourth attribute. So let us take only 4. 0 to n minus 1, let us take only 4, n is equal to 4. Educational background, cultural background, societal background, financial background. And suppose you are standing in a queue. While coming to the university, you are standing in a queue in a metro. And there are, say, 4 such persons or 5 such persons standing in the same queue. And each of them, they have the different amount of this cultural, societal, financial, and academic background. So the behavior of each of you to that particular system will be different. It is based on the different components already present inside you. Suppose the metro is led by say 20 minutes, or the metro is led by say 10 minutes. That is the behavior of the system, right? The way you behave and the way the other persons behave, they're completely different. That entire, this entire final behavior after you come out of the metro station and your entire emotional condition, physical condition, mental condition is governed by what? Is governed by the system itself as well as the individual components which are already present inside. There could have been 100 such persons riding the same metro, but they have their different components, different attributes. So their behavior to such a system would be different, and accordingly, so now if I would like to interpret your behavior, then it will be easier for me if I segregate you, if I regard you as a signal, and if I segregate you as the components of different attributes. Your academic attribute, your financial attribute, your cultural attribute, as well as your societal attribute. And accordingly, the final behavior that you render over there is a combination of all this. The way the HR manager, behaves with his or her subordinates, basically it's a combination of the different attributes that the person possesses. It's a combination of all those. The academic, educational background, the societal background, the cultural background, the financial background, and other background as well. So, when I observe the signal in this perspective, so basically I am breaking the signal into different components, and I can interpret and I can process that particular attribute in much elegantly. And that is the basis of any frequency response of any kind of system. If you open any book on signals and systems or digital signal processing, you'll see that the expression for the Fourier series is given by this one. The expression for the Fourier transform is given by this one. The expression of the Laplace transform is given by this one. That's a mathematical expression altogether. But until and unless you understand the philosophy behind this mathematics, because I've told you, the ultimate degree ends at philosophy. The final degree. You know, doctorate in philosophy, right? PhD. So everything ends at philosophy. So you need to understand the philosophy behind this mathematics. So whenever you observe this as a frequency, that's a mathematical stuff altogether. But when you visualize, no, it is not only mathematics. These individual frequency components can be regarded as the attributes. And let us try to personify you as a signal. You can have infinite number of such attributes. I have mentioned only 4. Then your behavior can be judged to any particular environment. Suppose the metro is late by 10 minutes and you have to attend a class test here or viva over here, then your behavior will be something different as compared to when you attend a normal class over there. It also depends on your financial condition. If you can afford a cab, suppose you come, say from, if I consider, now the nearest metro station is very nearby. If I consider, say, our Jadavpur University main campus, then the nearest metro station is Tollyganj or Ravindra Sarovar. So even if you are late, and if you can afford a cab just outside the metro station, then your behavior will not be that much. Will not be that much arrogant. Aggressive can be arrogant. So it's a combination of all these. Right? So the way you behave is the composition of the different components which are already there inside you. So you are treating yourself as a signal. Right? You are personifying yourself as a signal. And let us try to visualize the signal from this perspective. So signals, they are also having the different variations. When you listen to any band performance, right? So there are different types of instruments. What you are perceiving the complete environment, the complete sound you are perceiving. But remember, within that orchestral performance, you have the drums, you have the flute, you have the guitar. So all the different instruments are there. And what you are receiving the final output. It is composed of different instruments. You have the drums being played, flute being played, sitar being played, guitar being played. So there are different instruments, and all these different instruments, they have the different frequency components. Drums have the lowest frequency components. Flute, they have the high frequency components. Guitar, for example, sitar, if you consider that they have different frequency components. And when you perceive the final sound, that's a combination of all these different frequencies. So here you can directly connect the frequency. Okay, low frequency, high frequency, mid frequency, you can directly connect. And as far as your behavior is concerned, there also we have different types of attributes. So that's a very elegant way to observe the signal. And your output is basically the summation of all these different. So instead of representing it by means of only delta function and the shifted delta function, if you observe the signal from this perspective, it will give you a much clearer picture towards the field of signals and systems. Okay, so we have already discussed the first one, that is a discrete time Fourier series representation for the periodic signal and the discrete time periodic signal, and still the other parts are also left, and that we will discuss in the next class.